Good evening, friends. Welcome to Manthan once again. Today's topic for discussion is all about black holes, what black holes are, and what are the various features of the black holes. To define a black hole, it's a celestial object from which no one can escape, not even light. That is why it is called as black hole, because it looks black in the outer space. Now, we will also try and understand how black holes are created, the science of collapse and the core mass, how they decide how the black hole is formed. And then we will try and understand what the structure of the black hole is. And before understanding what it is, let us understand what it is not. And then we will study about the various areas of the black hole, like accretion disk, horizon, and mass. And then we will try and consider what would be the black hole mass be made up of, what is its constitution. We will try and propose a concept of monoatom. And then generally black holes are considered as, weighing those many sun masses. We do not differentiate between the mass, but we will try and see if in a black hole a mass can be differentiated. The mass of the black hole can be differentiated. Then generally it is said that the shape of the black hole is spherical. Manthan model will question it, contest it, and suggest another model other than sphere, and provide sound reasoning also as to why we say so. And then we know that black holes are not stationary objects, they do move in the galaxy or in the universe. So we will see what are their travel habits. How do they move around in the galaxy itself, and we will also show that possibly all these black holes, once they form, they have nothing but no other choice but to move to the center to meet the supermassive black hole at the center. And then we will try and address a few contradictions. Generally it is said that galaxy cannot survive without a supermassive black hole at the center. The very existence of supermassive black hole, the galaxy itself is because of supermassive black hole. But we will try and prove that galaxy can survive a supermassive black hole. Even if it is not there, it can still survive. Then we will take a few theoretical conditions wherein we will try and show that classical model of universe does not, it fails to accept such kind of a model. But when it comes to spacity or Manthan model, we will be able to explain such kind of theoretical galaxies. So let us go to the first part of it, whereas how black holes are created. Black holes are created when a star dies. So every black hole that you see, it once was a star. So for us to understand how black hole takes shape or forms, we need to understand the life of a star. And every star has got a limited life time. Like our own sun has around 10 billion years of life. And now this star's age is defined by the science of collapse and the core mass, and we will study both of them. The science collapse in the sense the star is made up of a core and an outer mass. And this core is where there are nuclear reactions going on. These are basically fusion reactions, and these nuclear reactions are the ones which are generating tremendous pressure and temperature. And in a way they are generating an outward force, and this outward force acts as a balance for the star mass from the outer mass collapsing on itself. So there is a kind of an equilibrium which is maintained between the core and the outer mass. Now obviously for a fusion to happen you need fuel. So it all starts with a simple molecule of hydrogen as fuel. So as and when hydrogen is fused into helium, and then hydrogen gets used up, helium starts getting fused, and like that you move on the periodic table to higher molecular weights. And all these processes are exothermic in nature. They are releasing energy, and as long as that is happening, there is an equilibrium between the outer mass and the core. But moment you reach iron in the periodic table, the fusion to to achieve an iron core is not an exothermic reaction, it's an endothermic reaction. It consumes a lot of energy. It's an energy guzzler process. That is when the engine shuts down. That is when the core shuts down of the star and the star collapses. And when the star collapses, not that every star which collapses ends up as a black hole. There is a particular criteria which is defined by Chandrasekhar, the scientist. It's known as Chandrasekhar limit. If the core mass of the sun, of the star that is collapsing, if it is more than twice the sun's mass, then it turns into a black hole. Anything less, it could either be a neutron star or a dwarf star. A sun like ours ends up like a dwarf star. And majority of the stars that we see in the night sky, they end up as dwarf star, more than 90%. Less than 5% end up as neutron star, and only 0.1% of the stars that we see in the night sky end up as black hole. That's a very small percentage, but if you look at number of stars in our own Milky Way, around 100 billion, 1 in 1,000 would turn out into a black hole. That would be millions of black holes. That yields millions of black holes. So that is not a small number. Now let's go and check on the structure and the shape. Now, as I said, before we go and see what it is, what a black hole is, let us see what it is not. It is generally said that when the star collapses, it collapses to a point where all the mass is represented in a zero volume and in infinite density. When we say zero volume, which means that mass does not exist, which means all the mass that was there from the original parent star got converted into pure energy. That is the only way. And one thing for sure we should understand, black hole is not pure energy, it is just mass. Why do we say that? If it was a pure energy, it would not have attracted the masses the way a black hole does. So if you have a black hole and you have a star nearby, it gets shredded, it gets attracted. So for this to happen, the black hole has got to be a mass. It's a densely populated, densely packed mass, but for sure it is mass, and it is not pure energy. Energy is unitary in nature. It has the habit of dissipating. Its idea is to just dissipate itself. Entropy is increased, but the energy does not affect another blob of energy. It is also said that black hole is a tear in fabric of space-time, especially when you have huge mass concentrated in a very small space. It is said that it kind of tears the fabric of space-time. It does not. There is no tear, because if there was a tear, when the black hole moves, the space would have had any kind of effect. But as you see, space behaves as though nothing has happened to it. The black hole comes and moves, but the space remains as it is. It is not just small black holes. Even if it is, you consider a supermassive black hole, it may be stationary with respect to the galaxy, but when you consider the whole galaxy itself moving, even the supermassive black hole is also moving. So 2 million suns of weight in that position is moving, but it is not tearing any space. So it is not a tear in fabric of space-time. So now let us understand what are the various areas of black hole. So let us try to move from outside towards inside the black hole. So when you are outside the ring that I have shown as an outer ring, you are safe enough, in the sense you are far beyond the influence of black hole. You will not be sucked in, or in any case you would not be affected. But as soon as you come in this band, which I have shown as accretion disk, that is where the mass gets heated up. That is where you are coming into the influence region of the black hole's power, and that is where the mass gets heated and it gets lit up, and that is why we see in the accretion disk in our telescopes, and that is why in the accretion disk you have the mass being seen. But what happens in this inner ring, which is called as horizon? Once you cross this, There is no way of coming back. That is where it is called as horizon, is because nothing can escape the influence of a black hole, not even the light. As long as you are in the accretion disk, maybe you have a chance to spend energy and escape. But once you cross this horizon, whatever kind of energy that you use, you just can't escape, because you need to travel faster than speed of light. Nothing can travel faster than speed of light, and even speed cannot escape. And that is why you have a horizon. And once you cross the horizon towards the center of the black hole, you do not immediately encounter the mass itself. It is much, much farther away, which, as I have shown here at the center, that is where all the mass is accrued or is deposited. Now, coming to the constitution of the mass itself, generally the classical model of universe says that this black hole is 2 million sun, it's weighing as much as 2 million suns or 1 million suns or 100,000 suns. It does not make a difference differentiate between the type of mass that the black hole is made up of, which we will try and do now. So what exactly is this mass made up of? First, we will consider the mass, which is a native mass, the mass that is related to the parent star that collapsed into a black hole. So try and imagine you have a mass of the star, whatever be the type of element that the star is made up of, it is collapsed into a small area which would be under tremendous or infinite pressure and infinite temperature. At that stage, what would happen to that element that made up the star? Whatever it be, whether it is proton, neutron, electron, and quarks, they would cease to exist. In the sense, they would be shredded. But shredding says that it is moving out, but that doesn't happen so. The enormous energy of the collapse of the star's mass would pack it up into a blob of homogeneous mass. In the sense, this also is a mass which doesn't have, usually when we say a mass, it is an element, it has got a proton, neutron, electrons. There would not be any element like this. It is just pure mass which is going to be formed into a blob of homogeneous mass. This is what Manthan proposes. This is almost like a monoatom. The whole mass of the black hole itself, the one which is related to the star collapse, it acts like just one single atom. As though you have a periodic table, you have molecular weights going up to the last one. This one would be the grandfather of all those atoms. Just one atom and tightly packed mass. And then why we talk about the types of masses, basically just now we learned that for a black hole to form out of a star, you have to cross that Chandrasekhar limit, which is the core mass equivalent to around 2 suns. But we have seen supermassive black hole which weighs around 4 million suns. It's as heavy as 4 million suns. So where did all this mass come from? Agreed that it could have started from a higher or a bigger star. The 2 suns is the basic minimum. Anything beyond that, it becomes a black hole. But what could it be? How heavier could the sun or the star be? The supergiant star that we have come across in the universe is weighing not more than 300 suns. So you can imagine where 300 suns is and where 4 million suns is. So quite a bit of black hole's mass is acquired mass. So we differentiate it as native mass and acquired mass. Native mass is the one which is monoatom, which is packed, solidly packed, whereas acquired mass is the one which it has acquired through eating all these various stars, planets, and the gas material around it. It is like in a fruit you have a seed and a pulp. So pulp is that acquired mass and the seed is the one which is the native mass. And native mass has far more effect on pulling matters towards it rather than the pulp. The pulp, of course, it is also powerfully packed because it is going under immense pressure. But all that pulp is going and sitting on the native mass. And one thing that we should understand is there is a no entry board for this acquired mass. Of course, it goes and gets stuck on the native mass, but the native mass is so densely packed and it is a single atom, there is no way the acquired mass can enter the native mass. So when you take a cross section of the black hole, you will see the outer part, which is acquired mass, and the inner part, which is the native mass. Now coming to the aspect of what is the shape of that black hole mass. Of course, we have already shown it as spherical, and is it really spherical? Manthan model will contest that, and we'll say that it's not possible to be spherical, and we will also suggest an alternate model for that. Now let us assume that what classical model is saying is right, that black hole are spherical in nature. The mass of the black hole is spherical in nature. If it were spherical, let us assume this is the black hole. Let us assume this is that spherical mass that we just discussed, and this spherical mass is that of the black hole. Now, if that were the case, the mass would be attracted to this black hole from every angle. All parts of the sphere, the mass would be attracted. But we do not see that. We see that there is only an accretion disk. In the elevation, you see this accretion disk, and in top view, you see that accretion disk. It is only a plane. If it were spherical, just the way you see the light, the mass lit up and seen, you would also be seeing all the mass which is falling into the black hole from every side, that will also be lit up. And what you would see is not an accretion disk, you would see an accretion sphere. You would not see an accretion disk or a plane which is going around, but you would see an accretion sphere. So in a sense, what would be a difference between a star or a black hole? When you see in the telescope, the star and black hole would look the same, because what you have as black hole would have all the masses falling onto it and being lit up. So when you look into the telescope, you would see that the star as well as the black hole are looking the same. It's only when you cut through the black hole, which obviously you cannot, but just in case, only then you would know that it has got only a cover and inside is all hollow. So that is why we say that it is not spherical. And this is an actual photograph it's an optical photograph of a black hole. And as you can see, you see clearly a black part in the center. If it was an accretion sphere, all of this would have the same similar kind of light even at the center. The fact that it is not shows that the black hole is not spherical in nature. This picture may be slightly misleading because you see this part, which as though the mass is moving from on the top as well as the bottom, but it's only the effect of black hole on the light being bent. So you have a black hole here, so you have a the accretion disk. So the accretion disk which is in the front is also lit up, and the one which is at the back is also lit up. The one which you see here is the one which you would otherwise not have seen. It is the accretion disk at the back. The light which is coming out of that is bent, and that is why the accretion disk which is moving from here to here is seen as though it is moving from here to here, and the same one is happening at the bottom also. So in a way, this is not the mass actually falling. The mass is falling only through the accretion disk. This one is only a mirage of the accretion disk which is behind the black hole. So let us assume that Manthan does not agree with the model of spherical black hole proposed by a classical model. what is it that Manthan model suggests? What shape would the black hole mass be? So this is the classical model, as is said, and this is what Manthan model proposes. It's almost like a donut. Of course, we will not just propose and walk away. We will give you sound reasoning. So let us go through each of the. So let us assume, to begin with, this is the star, which is perfectly spherical, and you want to collapse it into a smaller sphere, and that also should be spherical. Just the way this is an exact sphere, the end result also should be an exact sphere. That is possible only when the collapsing force which I am applying at every point has got to be same. As is shown there, every arrow which is towards the center should be equal in magnitude. That only then and only you would end up with a quashed sphere, a quashed star, which again is a sphere. Now, for this collapsing force to be same, what is most important is that the mass distribution should be uniform. And what is the mass distribution in a parent star? This is what a sun would look like, the cross section. The mass distribution is anything but uniform. So when you have a non-uniform distribution, the forces are not the same. So the collapsed part also will be anything but spherical. Now that is one part. That is a proof to show that the collapsed mass is not spherical. But how does it attain the quashing effect? So when you have an unequal mass distribution, you have differing forces. Let us assume there are two differing forces. The collapsing force. One is the primary force F1 and another is the secondary force F2. They are massive, both of them are massive in nature, but one is higher than the other one. So possibly, as can be seen, the one which is shown vertically down is bigger and the one which is shown at the side is smaller. That is when it gets squashed to reach a donut-like shape. But one may say that that is okay in theory. In reality, it is not necessarily that the collapsing forces as shown as F1 and F2 are just two types, or for that matter they are that exactly 90 degree. It could be F1, F2, F3, F4, because this is a very dynamic situation. That the mass distribution, there is no theory to it, there is no science to it, and plus it is dynamic, it is changing. So one may say that it may not be a perfect sphere, but it could be an irregular blob. Not a perfect sphere, but it is an irregular blob. What we should consider here is the spin factor. What I mean to say by spin factor, let me explain it this way. Any geometrical sphere that you take, there would be only one center. Center is a point from where every point on the surface of the sphere is at equal distance, a distance of r that we know as radius. If you replace that with a spherical mass, even this also has a one center. But there is a condition to that. Precondition is that the mass that you are considering should be uniform. Every constituent mass of that spherical shape should be equally spaced, equidistant, and should have the same kind of density. Then only you can say that it is uniform. If it is not uniform, what happens to the center? The center gets offset. There will be two centers in that kind of a sphere. One which is geometrical sphere, another which is the center which takes into account the mass distribution also. When there is an offset and when you have these masses, when the collapsing forces are acting on the center, at a distance away from the geometric center, it creates a spin. And whenever there is a spin, there is an axis, major axis formed. And whenever there is a major axis, the mass rotates around that major axis. And this spin regularizes the shape. the shape which otherwise would have been an irregular blob now will be regularized to form a kind of a disc like a donut. Now, you may ask that, agreed, there is a spin and it's a galactic spin. Why can't we have a mass of the black hole, a thin paper-like disc rather than a thick disc like a donut? We should understand that we are dealing with black hole here, that the compressive force is far, far immense in nature. The F1, even if it is smaller, it still packs a punch. So it would not allow the thinning of the black hole mass. It would still be thicker. Then we know that we had shown in the structure, there is a hole at the center. If at all we are talking about such immense pressures of a black hole mass, it's almost impossible to have a hole at the center, because the pressure at the center is going to be the most at its peak. So why is it that we are saying there is a hole at the center? Now, this is what we are going to explain now. So we have two things to take care of. One is the collapsing force, another is the spin. There for sure is an effect at the center. It could just be a dip, or it could be a through and through hole, or it could be a bigger size hole. But whatever it is, there is an effect, because agreed that the collapsing force is massive, but the spin is also, we are talking about the level of a black hole. The spin of a black hole is astronomical. It may not be able to change the outer perimeter dimension, but it is good enough to create a dent in the center. And that dent, as we say, could just be a dip or a through and through hole or a bigger size hole. So when we have two options, you could either have a barrel or a donut shape. Barrel you receive when you have as an end result when the spin is more than the collapsing force. When the collapsing force is more than the spin, then you have a donut kind of a shape. And why I say not just a dip but a through and through hole, size can be, how should we say, debatable. It's not a big hole, it could be a small hole, but for sure it's a through and through hole. We will discuss that in a later stage. You see the gamma rays and the X-rays, which are, whenever a black hole feeds or feeds on a star, it usually ends up burping gamma rays and X-rays at the center. It is generally said that it is not because of the mass coming out of the black hole, because nothing can come out of the black hole. It is that just the mass which is falling onto the accretion disk, that is the one which is coming out as a burp. But if you see, if the mass is falling here, why would it come out of this? It would come out only when there is a weakness there, and that is possible only here. This seems to be the weakness, where the spin, the centrifugal force, is pushing the collapsing force, and that is why. And the burp is not just one direction, it is in two directions, both up and down, and that is why we say it is a through and through hole. Debatable, but this is something which is what Manthan is proposing. And this we can use, we can exploit this as a weakness of black hole. If at all you want to send a probe, you know that side on would not be an admissible thing, because you have an accretion disk which is heating up the mass. So maybe this part is where you should send a probe in, because it is the weak point where you could possibly enter a black hole. But only thing you should be mindful of is the oncoming gamma ray train or X-ray train, because that could have crazy consequences. And in all this, what we should immediately that we should take notice of is, generally shapes do not change in universe. It takes millions and billions of years for shapes to form, to change, to make a difference. But in this case, from that stage to this stage, from the collapse of the equilibrium to formation of this force, it all happens simultaneously in a fraction of a second. So it's not that it is taking millions of years to happen, it all happens just like this. Now that we have understood what a black hole is, how its masses are properly how behaving, let us try and understand how the black hole itself behaves now as a unit. We had said that where there is a black hole now, there once was a star. So every star, that this is the galaxy that you see, this is the inner ring, this is the bar, this is the spiral arm. I have depicted the same thing. This is only a sectorial view. This is the inner ring, these are the spiral arms. So every star that you see here, if it meets the Chandrasekhar limit, has the possibility to convert itself into a black hole. Any star. So it is not just necessary that you should find the black hole only at the center. You could have the black hole anywhere in the galaxy. Wherever it meets the limit of Chandrasekhar, it could turn into a black hole. And what happens to that black hole? And we know that black hole is nothing but mass. Star is also a mass, black hole is also a mass. So why should why should universe treat black hole any differently? It just treats it like a mass that is tightly packed. So the black hole, if let us assume this one particular black hole is formed, it follows the same route as its parent star would go. So it would also go around the center, keep going around the center. But we also know that black holes feed, they bulk up. Agreed, we have minimum requirement of 2 suns, the core mass of the star which is collapsing. But we have seen that the black holes are many hundreds, thousands of suns. So how is it that it is able to bulk up? Especially when it turns black hole, the immediate meal that it has is possibly the planets near to it or its own planetary system, the gas around it, at the max a companion star or a binary star. Apart from that, the closest meal that it has is many light years away. The closest that Sun has as a star is Alpha Centauri, that is around 4 light years away. So it would be very difficult for black hole to bulk up, but for sure we know that it is it is bulking up. So that means there is something that is happening that is making the black hole either speed up or slow down. You either have to go and catch the meal which is in front of you or slow down and catch the meal which is coming towards you. But why should black hole have this luxury when it is just a mass like star? Star doesn't have the luxury of speeding up or slowing down. So why should black hole have? This is where the Manthan model, the spacity model comes into picture. So in Manthan, the spacity model, whenever you have a system of masses which is more than 2, 3 or more, and they are in an orbit, they are subjected to a force called S3, which is acting in the general direction of the movement of the mass. Now what happens is, let us assume that one of these stars has one black hole. So most probably the black hole mass is less than the mass of the parent star. So this is what it is. And then there is something called as average orbital mass. So we see these stars, I have shown them as all similar stars of same shape or size, but that need not be. Some star could be smaller, some star could be bigger. So there would be an average orbital mass. If the black hole which is created, if that is more than the average orbital mass, then the S3 will not be able to move the new black hole just to the same extent that it was moving the parental mass. But since the black hole mass now is less than the average orbital mass, then this S3 would speed it up. S3 is general and it is common to all, irrespective of what the mass is. S3 is directly proportional to the average orbital mass. Now what happens is, this is giving the black hole a chance to either speed up or slow down. So that is how it either consumes the star in front or consumes the star in the one which is lagging it. But imagine, take it a little further, let this thing run around for 1,000,000 years. The black hole which is eating these two up, it would eat all of them. So what would happen is, if there is a black hole forming in this orbit, over millions of years it would clear this up. You should be able to see, just the way you see Saturn's rings, you should be able to see the rings in the galaxy, and we see that that doesn't happen. That means the black hole is not staying in the same orbit, it is moving out of that orbit. Now what are the options for the black hole to move out? Either it has to move to its left or to its right. When I say right, it is moving away from the center of the galaxy. When it is moving left, it is moving towards the center of the galaxy. Where would it move? In or out? For that, we need to understand what is a galactic gradient. What you see here is a top view of a galaxy, and this is shown as though all the constituent masses are in the same plane. It is not so. If you take an elevation or a cross section, this is the supermassive black hole. The black hole which is formed here or here is not exactly at the average plane. Even if it is a few millimeters away from this, that is good enough for a gradient to form. And this gradient, imagine if this black hole has to negotiate this gradient. If it wants to move out, it is like climbing up the gradient, climbing up the slope. And this black hole doesn't have the energy to climb up. Unless until you have energy, you cannot climb up. And it is not just the black hole on this side. Even if it is on the negative side of the black hole, even moving out would be climbing up the slope, because there is no up and down in absolute space. Just the way this finds difficult to climb up, even this would find difficult to climb up, and the only way for them is to climb down or move towards the center. Now what happens when it is moving towards the center? Let us assume the black hole that we are considering was in the 4th orbit, that has moved to the 3rd orbit. Obviously, when it moved from 4th to 3rd, the average orbital mass was more than the black hole, less than the black hole mass. That is why it moved down. When it could not survive the 4th orbit, it will not survive even the 3rd orbit also, the next orbit. And if the same thing happens to the 3rd orbit also, in the same way it keeps sliding down. Once it moves out of this orbit, it is downhill all the way till it reaches the supermassive black hole at the center. That is how the black hole which is there at the center becomes a supermassive black hole to the extent of 4 million suns. You do not see a black hole which is 4 million suns somewhere in the inner ring. You will see that supermassive black hole only here. That is because every black hole which is formed here in the galactic rings, whether it is inner ring or the spiral arms, everything slides towards the sink of the galaxy and creates the supermassive black hole. Now there could be, and that is why you see black holes near the supermassive black hole. It's not necessarily at the center, which means that it is still on its way to, in a few million years, it would reach the center. And what would be the path taken by the black hole from where it generated till it reaches the center? It could be straight down, it could be lunging forward, or it could be lagging backward. It all depends on where it was, what was its mass, which orbit it is moving, what was in its vicinity. Accordingly, the path would be decided. And these are basically the travel habits of as proposed by Manthan. Now, the last section that we are going to consider is the contradictions of black hole. It is generally said that the galaxy cannot survive without a supermassive black hole, because classical model of universe says that it was the supermassive black hole which created the galaxy in the first place. So if you remove it, then the galaxy would disintegrate. To try and explain you a bit more Newtonianly or with Einstein's formula, what you have is you have two basic masses, and Newton says that there is a force of attraction which is known as gravity between the two masses, which is directly proportional to the two masses and inversely proportional to the square of the distance that separates it. So bigger the mass, the stronger the influence, and farther it is, lesser is the influence. The same thing is, the gravity is slightly differently formulated by Einstein, who says that every massive mass has the tendency to bend the shape of the space around it, and the space which is bent so, in turn, guides the smaller masses how to move around it. So what it is saying is that when you have a larger mass, it is bending the space, and the bent space is telling this particular mass how to move around it. In the sense, if this is a bigger mass, then this would be closer to it. If it is a smaller mass, it would move away from it. So this is what we say: larger the mass, steeper the gradient, stronger the influence. Alternately, smaller the mass, gentler the gradient, weaker is the influence. So it looks so commonsensical that if this is the mass which is holding this mass in position, you take this away, the supermassive black hole, from the center. This mass, there is no one to guide it, though there is no one to have a hold on it. It is free to move. And that is how it is said that when you have this galactic mass, all the stars going around the supermassive black hole, it is the supermassive black hole which is holding them in place. You take out this supermassive black hole, the stars would feel free to fly away in a direction which is tangential to wherever they are, and the whole galaxy would disintegrate. We will also remove the black hole, but we will not remove it right away. We will reduce the size of the supermassive black hole. We know that it weighs 4 million suns. Let us, as an experiment, just take one sun mass out of it. Now the supermassive black hole weighs as much as 3,999,000 suns. What happens to the galaxy? So we have made this supermassive black hole slightly lighter. The influence will be lesser. So the mass which was here would move out. This would, all the stars would move out slightly, maybe a millimeter, maybe less than that. But the stars are not flying away, the galaxy is not disintegrating. Let us go one step further. Now let us again remove 100 sun masses from the supermassive black hole. Now again the influence decreases a bit, but the stars don't fly away, galaxy doesn't disintegrate, the galaxy size increases. The shape is the same, but the size increases. Let us now cut it into half, 2 million sun masses, the supermassive black hole. Again, the stars are not flying away, the galaxy is not disintegrated, but now the size of the galaxy is supersized because the influence is less, but the galaxy is not disintegrated. You can keep doing this till you come to a situation where the black hole at the center is just one sun mass. Even then, the stars would be going around. They would not be flying away. The galaxy is not getting disintegrated. So even when you remove that one last sun mass weight, even then the galaxy would keep on following the orbit that it was. It is just that it is bigger in size. And this is the contradiction that we talk about. And how does spacity take care of this? Spacity fortunately has got S3. And as you can see, S3 does not need a mass at the center, whether it is supermassive or any mass. If it is there, it is good. If it is a supermassive mass, then the orbit reduces. But it does not depend on a central mass at all. If you remove this central mass, the S3 would keep these masses in orbit. Now one may say, if at all the galaxy can survive the supermassive black hole, how did the galaxy form in the first place? You could visit my previous videos related to early universe, how the galaxies were formed. We explained how galaxies can form without the use of gravity, without the use of a supermassive black hole at the center, without the use of dark matter. We just used the highly ionized charged particles that the gas would be to begin with in early universe. You can visit that video and it explains all these situations. And the next contradiction that I want you to talk to you about are theoretical in nature. But you know, whenever we propose a theory, theorem, it should be applicable both in theory as well as in practice. The assumptions that we are making here is, you see all the constituents of this mass, of this galaxy, which is basically the stars in the inner ring, stars in the spiral arm, and the supermassive black hole at the center. Now, what happens? Does the classical model of universe, which is based on Einstein's general theory of relativity, of the massive mass bending the space and the space guiding the smaller masses how to move around, does it allow for a model which has the black hole as one sun mass and each star that you see as equivalent to one sun mass? In the sense, any mass that is there is the same everywhere. What would happen in a classical model of universe? You have the supermassive black hole at the center, you have these stars, the space that this star, the sun which is bending, would have no effect on these stars at all, which would as good as to say that these masses would be free to move and this whole galaxy of this model would disintegrate. Such a model is not possible at all. Such should not be the case. Theorem should take care of whether the supermassive black hole, small, big, small, small, all possible cases should be applicable. This is what happens in spacity. The Manthan model, which depends on spacity, has got S1, S2, S3. S3 takes care of these, keeping these masses in orbit. You can visit the previous videos of why spacity. It tells you the mandate of spacity is to act on the mass or every form of energy. Mass being another form of energy, it is acted upon. If it is, and how it acts, it depends on the state of the mass that is in. If it is 1, then it is a compressive force. If it is 2, it is trying to bring them together to make it 1 and then act on it. If there is a system of mass already acting on it, then it is acting in the general direction, because the mandate of spacity is to keep the masses in the huddle, because if it is acting in any which way, the masses would fly away. So in this case, S3 would still act on these and make this galaxy work. So that is why we say that the classical model of universe has got a contradiction, which Manthan model clearly explains. The third case or the contradiction is merging of twin black holes. We all know merging of black holes. So you have two black holes, they just come and merge. But this again is theory. This never happens in reality. Let us assume you have a black hole. I, through magic, may create another black hole which is exactly a replica of the first black hole. Don't ask me how, it's magic. I have two black holes which are exactly similar in every size, shape, matter, density, intensity, whichever way you compare them, they are twin in nature. It's as though, you know, Control C, Control V. You take one black hole, copy paste it and make another black hole. Why do I say twin black hole? What happens? how do they bend the space? Each would bend the space exactly in the same way as the other one does. If the gradient of this is x, the gradient of the other one is also x. And we are assuming that this universe, in this theoretical universe, there is only these two twin black holes, nothing else to bother them. So the gradient would be similar. Now see what happens when these two masses are coming together. They are not coming head on, because if they are coming head on, they will crash. Let us assume that they are going their way off. Generally, what we have seen is these two masses, when they come, they should come near and then merge. But in this case, when the gradient is the same, this black hole will not be able to guide the other black hole as to how to move around it. If this was slightly lesser than that, this would tell it how to move around it. Now that both are same, both will not be able to have influence over the other. It is as though when these two masses are coming, they are blind to each other. They cannot influence each other, they just walk away. And we see that it doesn't happen so. This takes care of in Manthan model. How does that do? Manthan model, you can see S2, it does not make a difference whether it is equal masses or unequal masses. It just brings them together because it is operating from outside. So this is what I wanted to talk to you about black hole, the various aspects of it. Hope it was interesting. Thanks for watching.